I'm going to try to do a lesson on circular motion as I might do it in class. You'll probably know that my typing isn't brilliant, so prepare for some errors here. So let's consider a particle moving in a circle with speed v meters per second. So it's moving at a constant speed. Notice I'm talking speed here, not velocity at this point. So since the direction of the particle is changing, then the velocity is changing. Because, of course, velocity is a vector. So, if the velocity is changing, then it must be accelerating. There we go, my typing again. So there is a resultant force. Okay, so there's your recap of GCSE, really. Particle moving in a circle with a constant speed. I should have said constant there perhaps, just to make it clear, although since I said it was V, it should be clear that it's constant. So it's moving at a constant speed, v meters per second, in a circle. Because the direction of the particle is changing, the velocity is changing, because velocity is a vector and therefore it is both magnitude and direction. So the particle is accelerating. Because it's accelerating, there must be a resultant force. That's Newton's second law. That is to say, the rate of change of momentum is proportional to the resultant force, and momentum is mass times velocity, of course. So let's look then at modeling this. So here we have our circle. I have field to mark my radius in as r. So we have a circle, radius r meters. So if we measure this angle swept through, so in a time t seconds, the particle moves through an angle theta radians. So it goes from here to here in t seconds. The length of the arc swept out here is r theta, if theta is in radians. Just in case you're unfamiliar with this, 360 degrees is 2 pi radians. Oh, hang on. Let's change that. Back to aerial. Oh, wow, okay, 360 degrees is 2 pi, and let's change that back to radians, sorry, aerial again. That was unexpected. Oh, okay, interesting. So that should be, that'll do for that, 2 pi radians. Just in case you're unfamiliar with that, I'm not quite sure why this is a different font. I want that to be Arial. I prefer Arial. Okay, so there's your relationship between degrees and radians. And again, we're back in symbol. Okay. So the benefit to us here in measuring the angle in radians is that this arc length here is r times theta. Now, if you think about it, the circumference of the circle is 2 pi r, you know that. 2 pi being the number of radians in one circle. So if it was half a circle, a hemisphere, it would be pi r, because the angle swept out going from here to here is pi radians. So you see the connection between your circumference is 2 pi r and your arc length is r theta, I hope. So v then, the speed, would be given by v is r theta over t, that is to say, the distance travelled divided by the time. So we have a new term, a new quantity, which is angular speed, the angle swept out per second, which is omega, pronounced O-M-E-G-A, and that is not a W, it is an omega. And we have omega is theta divided by t, where theta is in radians, of course. Hopefully that's obvious, but I'll say it just in case it's not. So theta in radians. So that leads you then to, if you look at omega is theta over t, and v is r theta over t, then v equals r omega. So your first gotta know equation, I say gotta know, of course it's on your data sheet, but I really think you ought to know it, is that. And we also have the relationship that omega is 2 pi over t. Again, that should be a capital T. That should be fairly obvious, where t equals the period in seconds, and the period is the time it takes to make one complete revolution. Sorry. So hopefully that's fairly clear. So then, a variation of that same equation, which you might like to have t is 2 pi over omega. So you have v equals r omega, the relationship between the linear, hang on, let's get back into Arial again. So this relationship connects linear and angular speed. Okay, so we have a particle moving in a circle with a constant speed, radius r. We have established that because the direction is changing, the velocity is changing, therefore it's accelerating. So there is a resultant force. If we then model this and we say, well, here's our circle, radius r, and we're starting at t equal to 0 here. Sorry, I couldn't manage to make the diagram say all this. I'm not really very good at this sort of thing. So the radius r starts here, traveling with speed v. This is my the direction of my velocity, actually. So it's doing v meters per second in this direction at this point, v meters per second in this direction at this point here. So in t seconds it gets from here to here. In t seconds it has swept out theta radians. And so it has traveled r theta meters in t seconds. So the speed is r theta over t. Theta over t is the angle per second, that's our angular speed. So then we have, combining this equation, theta over t, and v equals r theta over t, we get v equals r omega. Omega, the angular speed, of course, is one circle in the time it takes to sweep out one circle, which is the period, which gives us the period as 2 pi over omega, just rearranging that equation. It's important, I think, that you understand this rather than trying to learn it as such. But there you have your basics then of circular motion.